Well, hello, students. How is everyone doing today? Well, today we'll be going over the kinetic molecular theory of gases, which is basically kind of the ideal gas law. We're going to do a few simplifying postulates to help us in the start to figure out what exactly we're talking about and how to quickly understand it. These are just to make life simple. So the first one is a gas consists of a collection of small particles traveling in straight line motion and obeying Newton's laws. So that means just the particles going to go back and forth and back and forth. The next one is there are no attractive or repulsive forces between particles. So that means they're just going to stay kind of put. And then collisions between molecules are perfectly elastic, thus there is no energy gained or lost during collision. So the kinetic energy is just equal to each other, so Ke1 equals Ke2. And that's kind of just to help simplify some of our stuff later on. The next one is the gas molecules in gas occupies no volume. Basically, that's just saying that the gases are just going to be a bunch of free particles in there taking up all the space. And it's kind of showing just little particles, bang, 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 many particles popping up and moving around. But there's no complete volume change. So they can kind of go anywhere they want. I mean, they're just going to be moving around and such. So that is the fourth one. So the fifth one that will be coming up here is that the average kinetic energy of a molecule is equal to 3/2 RTN, where R is the gas constant, N is just the number of molecules, and T is the temperature range that we're going to be using. Next, we will be talking about the macro and microscopic scale.
Some of the microscopic properties include pressure, volume, and temperature, and they are a result of the microscopic properties such as position and velocity, which this little V down here is the velocity. So the gas molecule is consisted of different molecules that are moving around constantly in the unit square. We assume the molecules do not collide with each other, and if they do, we assume it is an elastic collision. We are able to find the macroscopic properties through the microscopic properties. Now we're going to go over the ideal gas law, which is PV equals nRT, where P is pressure, V is volume, N is the number of molecules, R is the gas constant, and T is temperature. So we are just going to start with a simple monoatomic example where we have a molecule that we are going to be moving at a certain velocity in the x direction, and as it hits the wall, we're going to assume it's elastic and that it's bouncing off the wall with the same amount of velocity as it was moving towards the wall. So we're going to start with force, which is equal to the change of momentum and the change of time, which we can simplify to which is equal to m times the change of velocity over delta t. And since we know that the change of x, or the velocity of x, is the same both ways, we can change the delta v to say mvx squared over 2, and we can change the delta t to L since all of our lengths are the same. Since gases have more than one molecule, each of the molecules are going to have their own velocities that need to be accounted for. So when we are writing our force equation, we need to remember to add all of the velocities. So we're now going to have force equals mass times v1 squared plus v2 squared. And that's all going to be over L, which is our length for our unit square that we have. We need to make sure that we are accounting for all of the velocities of all the molecules in there. So we are going to divide by n, which is the number of molecules. So we're going to divide both sides by n to get an average velocity, which will make our new equation force over number of molecules equals to the mass over the length times the average of the velocity squared. And right now we are only looking at the velocity in the x direction, make it a little easier for now. So we have x is equal to n, so we're just multiplying it over, times the mass divided by the length, again multiplied by the average of the velocity in the x direction squared. And we're going to divide both sides by a so that we can convert our equation into pressure. So we know that pressure is equal to force over area. So now we have pressure is equal to the number of molecules times the mass divided, or times the average of the velocity in the x direction squared, all over L cubed, which we know is equal to the volume. So this is where we get our PV.
So now that we have PV, we can relate this to a three-dimensional box. So we'll have the number of molecules times the mass times the velocity squared of the sum of velocities squared. And this we could set this 3 times v x squared equals the v total squared, the summation of those. And this is showing that in 3 dimensions we kind of have the total of Vx, Vy, and Vz all kind of adding up to equal this PV. So now we'll have PV equals n m over 3 and the V total squared. So now that we have this, we're going to kind of simplify stuff. So the 3, we can move over the 3 to the other side, and we'll have n m to the v total squared. And so we're going to times both by 1/2 to get these kind of equal to each other. So now that we have this 1/2 m times v total, it can equal to our kinetic energy, the average of it. So once we have our kinetic energy average, we will kind of get this over into the ideal gas law. Because previously said 3/2 are Tn equals Ke, we can now put it into the equation. So we'll have a 3/2 PV equals n times the kinetic energy average. And once we put in the 3/2 RTn, we will come up with PV equals nRT, and this is the ideal gas law. So why we can use this is because the NK kinetic energy average is equal to the thermal energy of a system, or the total thermal energy of the system, which is also equal to Ke average. Why? Because n is out. There we go. So this is kind of the basic stuff of the kinetic molecular theory. There's more to it if you want to look into it, but that's the overall gist.